Good morning, everyone. Welcome. I hope that you can hear me. We'll start our lecture last week, I believe. On Monday. Yeah, it's not last week. On Monday, we looked at some MSI logic circuits. I think we looked at decoders, actually, just decoders. So today we are going to look at encoders, and then hopefully look at multiplexers. Now, just to jog your memory, decoders, you have some input and you want to generate one output that is equivalent to that specific input. So you can see that depending on what you have here, maybe 0, 0, 0, this is going to be, in this case, it will be high, the rest will be low. That means that you can easily look at the output and know what you are. Sorry, you can look at the output, yes, and know what the input is. If it is 1, 1, 1, everything will be low except that one, which will be high. That is to decode. Now we want to encode. Encoding is the opposite operation. With encoding, usually we have something at the output. We have so many possible outputs, and we encode an input that is equivalent to that output. Now, let's say that we have, say for instance, 8 separate inputs here. We can have a set of 3 outputs. When we were looking at encoding, we were looking at, say, 8 inputs, or no, in fact, 3 inputs, and we had 8 outputs. So now with encoding, this was decoding. So maybe you have 0, 0, 0 being represented by some output, Q0, 0, 0, 1 being represented by Q1, and so on. So these were a set of 3, a combination of 3 inputs. Now, another thing we looked at before was that for a decoder, we can have binary to octal, for instance. Here, we would have now an octal to binary encoder, or an 8-line to 3-line encoder. Before we had 3-line to 8-line decoder. Okay, so that shouldn't be strange to you. Let's look at an example so that we can deal with the real specifics of this. This, as you can see, has 8 inputs and it has 3 outputs. Okay, so this is a typical 8-line to 3-line encoder. So you have an output, you have an input here, and we want to know what it is equivalent to on the output. Say for instance, as you can see, all these are active low, all the inputs are active low. This is a special input that I'm going to describe. If you can see A naught, it's actually not connected to any gate. And so I'm going to explain that in a moment. But as you can see, it has 8 inputs and all of them are active low. That really means that usually they are high, because if they are active low, then they should be in the high state most of the time or during normal times. Now, let's, for instance, say that everything is high except A1. So what if A1 was low? If A1 is low, you can see that you have a low coming in here. And A1 only connects to that one. It does not connect to any other. If that is the case, then that means that you have a 0 coming into that bubble, which turns it into a 1, and this is an OR gate. So an OR gate, once it has a 1, it will return a 1. Obviously, these ones will return zeros. That means that when A1 is low, our output, which is O2, O1, O0, is equivalent to 0, 0, 1. Output O2, or we could say our Q2, Q1, Q0. So that is a bit different from the 0. If it was A2, which was low, what would happen? Now that means really that if it is A2 which is low, we have A2 going in here, and A2 does not connect to any other. That means in that instance that this would instead be 0, because we are assuming that A1 is high, meaning all these others are high, meaning that's a 0. This instead becomes a 1, and that remains a 0. So our output Q2, Q1, Q0 now corresponds to 0, 1, 0. And we can see where we are going with this. If our output, if A3, it is A3 which is low. For instance, if it is A3 which is low, by the way, this is an eraser. I didn't know that you can erase this. Very good. Okay. Wonderful. If it is A3 which is low, you can see that you have a 0 coming in here. Where A3 is connected, it's also connected there. And so that means here you'll have a 1, and behind the bubble you'll have a 1, but A3 is not connected to this, meaning you have 1, 1, 0, which means our Q2, Q1, Q0 is now 0, 1, 1. And we can see that A3, like in your decimal, number 3 is actually equivalent to 0, 0, 1. Let's do one more. Let's do like A7, A5. Let me rub that again. If we do A5 is low, you can see A5 feeds this one. So we have a 0 here, and also A5 feeds that one, which is a 0. So that behind here becomes a 1 and a 1. A5 does not feed this. So then we would have 1, 0, 1, which means that now our output Q2, Q1, Q0 becomes a 1, 0, 1. And we know that this is equivalent to decimal 5. So in other words, we have inputs here, which could be like 0, 1, 2, 3, 4, 5, 6, 7. And what we have at the output is a binary equivalent of that. In fact, some of these encoders, sometimes the encoders which do this are called decimal to BCD encoders. You have a decimal value, you can encode it into a BCD number, which is a binary coded number. By the way, let me let me insert a new. Generally, when we are encoding, this is what happens. For you who are maybe in telecom, those of you who have done something called, I don't know if anyone has done something called pulse code modulation. In parse code modulation, we do some encoding, and it's not so different from what we are trying to do here. In here, you have something, a process called quantization. I don't know if any of you knows about quantization, where you have a signal and you take samples, like that. And each sample you encode it with a signal. Usually you'd have quantized here, you can have your different levels. So between here and here is 0, 0, 0, 0, 0, 1. Okay, let me say 0, 0, 0, 1, 1, 0, and up here 1, 1. So that if this sample is in here, you encode it as 0, 0. If it's somewhere there, you can say this is still 0, 0. This one is in this level, 0, 1, and that one is in that level, 1, 0, and maybe you have another level there, another sample here, which is 1, 1. And then you are a signal. This is your analog signal, and your equivalent digital signal is now 0, 0, 0, 0 again, 0, 1, 1, 0, 1, 1. When you do this, you have encoded. What we have got is we have got a value that can be either decimal or some digit. It could be a fraction, a decimal number. And we have converted it into a code, a binary code, so you can based on its high on level. So when we are decoding within, when we are encoding within digital circuits, we have a signal that is coming in into the input, and output here we give it an equivalent code. That is why we said that when it is A1, usually A1 could be like a 1. Then we call that 001. If it is A2, usually that can be 2. We call that 101, 010. And if it is A5, we encode it as 101 because presumably this is like decimal 5. If it is A7, we can encode that as 111. That is precisely what we have just done. Now, the question might come, you might be interested in knowing why if A naught is not connected. Why is A naught unconnected? Now we said that all of these are active low, A naught unconnected. We can see that A1, in fact A naught to A9, no A7 are active low. That means that they are normally high. Now this is what we say, that when A1 to A7 are high, what are the inputs? What are the outputs of the encoder? If all of these are high, encoder output, which I can call Q2, Q1, Q naught is actually 0, 0, 0. But this is the output that we would expect if our A naught was low. You know, if our A naught was connected and low, we would expect our output to be Q2, Q1, Q naught being 0, 0, 0. So we assume that when all the other inputs A1 to A7 are high, meaning they are inactive, the output of the encoder is 0, 0, 0, which corresponds to A naught. In other words, even though A naught is not connected, whenever all the others are inactive, which is really the case for A naught, we still get the right output. And that's why they usually do not connect A naught, because that is the scenario for which all the others are high, and so the output is 0, 0, 0 anyway. Because you can see that when all these are high, all these inputs into the OR gates are high, are low, sorry, because you have a high coming in, which is inverted by the bubble, and then you have your output 0, 0, 0. So that's the reason why A naught is unconnected. It so basically says that whether A naught is connected or not, as long as all the others are high, we are still able to decode, we are still able to encode the value of A, which is output 0, 0, 0, which A naught would be responsible for encoding in the first place. Right. Now, we have a scenario where we could say that, let us look at the truth table before we go far. Let us look at the encoders truth table. Now we can see here that when A naught, with A naught we don't care because as you can see it's not connected anyway. But we say that this is the case really that I was talking about. When A naught is unconnected, we don't care. But as long as all the others are one, this scenario, as long as all the others are one, our output Q2, Q1, Q naught is 0, 0, 0. That is the case for A naught, whether it is connected or not. So that's why we do not connect it. Now for the next scenario, A1 is low, which means it is in its active state. But the others all need to be high, because if you have some others low, then you are you have a problem. Usually at the input, only one is active, all the others are inactive at the output, at the input of the encoder. This is opposite to the decoder, where at the output, only one is in its active state, only one output, so that it decodes what is at the input. Right, as we can see, when A1 is 0, we get that which we already saw up here. When it is A2, then all the others need to be high and so on and so forth. If you go to the case of A7 being 0, all the others are high. With A0, we really don't care because it is unconnected. We can see that we are going to encode A7 as 1, 1, 1. Okay. Now, the question might arise, what if A3 and A5 are simultaneously low? This can happen because of issues within the circuit. It might force one input to go low, like more than one input to go low. If you have more than one input slow or in their active state, then you have a problem. Let us look at this case. If A3 is equal to A5 is equal to 0, okay? What happens? Q2, Q1, Q0 is equal to, let us look at this case. We have A3 is low, so we have a 0 here, and we have a 0 here, and A5 is also low. So we have A5, we have a 0 here, and A5, we have another 0 there, in the middle there. Let me delete that. So for A3, it is there, and for A5, it is there. Now we can see that after the bubbles, we'll have 1, 1 here, which gives us a high. After the bubble, we have a 1 here. For the OR gate, we get a high. And after the bubble here, we get a 1, which gives us a high. Now, that means Q2, Q1, Q0 is equal to 1, 1, 1. Now, unfortunately, as we know, 1, 1, 1 is encoded for A7. The 1, 1, 1 is the code for A7. So your result is wrong on two levels. First, that your output does not correspond to any of the two inputs. Yeah, it is neither the code for A3, neither is it the code nor the code for A5. So we have a problem, and we need to deal with it. In scenarios like these, we have another type of encoder that we call a priority encoder. So we are going to now look at a priority encoder. A priority encoder is connected internally, it is connected in such a way that if a problem like that were to happen, where A3 is equal to A5 is equal to 0, then the output Q2, Q1, Q0 corresponds to the code of the higher value. In this case, the higher value obviously is A5. So our output should instead become 1, 0, 1. As we saw earlier, it became 1, 1, 1, which is obviously wrong. But if you have two or more inputs that are in their active states, in this case A3 and A5 are 0, then your output should become the output code should be the code of the higher input value. In this case, A5. The priority encoder has the logic internally to produce this output. If we look at this is actually the priority encoder. We are going to look at this in a moment. But if we look at this truth table, usually you have A0 here, but we know that in all cases, we don't care really what it is. Now, A1, because that is the case, this is the case for A naught. The first case is the case for A naught. As you can see, everything is high. And so our output is supposed to be 0, 0, 0, 0. The problem with this is that this priority encoder, which is the 74147, produces inverted outputs. This is a 4 output, it's a BCD output. So in fact, this is really a decimal on one side to a BCD priority encoder. Now that BCD code is generated in its inverted form. As you can see, inverted BCD. So we know that it is, the A naught would give us a code of 0000, but the output is actually 1111, which is the inversion, the inverted code for that 0000. Now, if we look at the next one, this is where things get a bit more interesting, and I want you to pay attention here. In this case, we have A9. As you can see, these are 10 digits, where 0, A naught obviously has been ignored, but it is there. This is the 10th. It's 1 to 9 plus that, which is 10 digits. That makes this one a decimal input. And that's why we have a decimal to BCD priority encoder. Right. Now, when A9 is 0, that means A9 is in its active state. We know that 9 is equal, when BCD 9 in decimal is equal to 1001 in BCD. Okay, binary coded decimal 9 is 1001. Our output is instead now 0, 1, 1, 0, which is just the inverted code of that, which is 1, 0, 1, 1, 0. Right. Now, however, what happens? You can see that as long as it's A9, we don't care what the smaller ones are, because with this a priority encoder, as long as A9 is low, even if any of the others were low, our output would correspond to the highest, which in this case is A9. That's why we put don't care states to the left of A9, because all those inputs are smaller than A9, and so they wouldn't override A9. In the case of A8, everything from A7 to A1, we don't care, because even if they were low, A8 would take precedence. However, A9 now needs to be 1, because if A9 becomes 0, then even A8 now is kicked out. So that's why A9 here is a 1. If we are looking at A7, when it is 0, A8 and A9 need to be 1, but the lower ones we do not really care. So this is a priority encoder where we realize that the output, as long as you have more than one inputs that are active low or they are in their active state, the output will correspond to the code of the highest input. If it is A9, all the lower ones, we don't care what they are. If it is A8, A7 to A1, we don't care. If it is A4, like in this case, it is A4, we don't care what A3, A2, A1 are, because they cannot override that. However, we care what the higher ones are, and in this case, we need to make sure that they are in their inactive high states. So in the case of, for example, this is what? A4. A4 is 1, 0, 0. No. A4, what is the code for A4? It is 0, 1, 0, 0, because that's 2 to power 2, which is 4. Right, so let us look at the code here. As you can see now, when we convert that, it becomes 1, 0, 1, 1. So you need to remember that the outputs here are just inverted. But if you, in circuits, when you want the actual output, you just connect inverters here, okay? And those will give you the actual BCD code, right? Okay, please, when you have a question, let me know. Otherwise, I will just assume that everyone is following. And if my network is not very good, once again, do let me know. Right. Let us look at this. I think this is what I've just explained, that you have 9 inputs and 4 outputs. These correspond to BCD, but in fact they are inverted. And these are your decimals. This is 1, 2, 3, 4, all the way to 9. And the 0 is not connected. Just one moment. Yeah, I muted myself because somebody just came into my office. I had to first chase them. Marvin, just to explain once again why A naught is not connected, because as you can see here, for instance, even in this case, A naught is not connected. A naught is not connected, but let's think, what would A naught help us? A naught would decode 0, decimal 0, which is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? These are our 10 inputs. Here they are called 9 because A naught is not there, so it is ignored. But let us consider A naught. If A naught was 0, we would be encoding, sorry. We would be encoding 0. But what is the code for 0? The code for 0 obviously is 0000. That is the BCD code for 0. Now, when A naught is active, is 0, all others are high, right? So let us look at the scenario of when all others are high. When all others are high, as in this case, our code is actually 0000. Obviously, in this case, it is inverted, but we can see that that is the code. In other words, we really don't need to connect A naught. As long as all the inputs, all the other inputs, all the 9 other inputs are in their inactive high states, the output corresponds to what A naught would give us. The code would correspond to what A naught would give us. So we might as well leave A naught unconnected. And if you can leave one input unconnected, it means that you have reduced the number of lines within your encoder, which is better. So that's, if it is useless, we might as well not connect it. But that's the reason why we do it. It corresponds to the scenario when all others are high. In other words, when we want to use A naught, just put all of the others, make sure all of your inputs A1 to A9 are in their inactive high states, and you'll get your code for A naught. Okay, that's why. How to solve the problem of simultaneous active laws, for example, A3 and A5. How, I don't know, Ian, if I understand your question, but I said that with a priority encoder, there is logic inside. In other words, it would be connected in a different way, but it has the kind of logic inside that enables it to give the code for the highest input in case more than one inputs. In case more than one input is inactive, is active. In this case A. Let us look at an example. What if A2, A7, and A5 were both 0? In this case, with the priority encoder, we know that A7 would take precedence, and A7 is called, the BCD for A7 is 0, 1, 1, 1, which means in this case, because it is inverted, it would be 1, 0, 0, 0. A7, let's see, A7 is here, and we can see it is 1, 0, 0, 0. But I'm saying, what if this was 0, and A5 was 0, and A2 was 0? If that is the case, we would still be able to get the right code, because the priority encoder would prioritize A7. That is why we say that we don't care what these are, since they are small and so have actually no impact or no effect on the output. Yeah, it is inverted, Emmanuel. Okay. Let us look at this. You don't have to read this. Now, this is called a switch encoder, and it uses our 74147. It uses this. In other words, we expect it that out here, it has inverted, these are inverted BCD, and that's why they've put inverters to give your normal BCD. So this is based on the inverter, on the encoder that we have just looked at. Now let us see on its inputs. These inputs are coming from, it is A1 to A9. Usually A0 would be here, but as you can see, it is not connected, okay? Because we know that when all the others are inactive, we encode for A0 anyway, so whether we have connected it or not. So we really don't need to. Now these switches are the ones that sort of, you can see you have 9 switches from 0 all the way to 9. So in fact, they are 10. But this one essentially may not mean much, because even if you can see that even if you press it, it connects this to ground. There is no connection here. So let us ignore that. Let's first switch for now. But this is called a switch encoder. In other words, it is the kind of, it's like these switches could be below your buttons when you are pressing on your calculator. And so every time you press a number, what happens? In their normal resting place, in their normal resting positions, you can see, before you press the switch, you can see that you have a high that is going into that input. And this is the same. The pull-up resist on each encoder shown only for this case. So you have a high connected to each one of these before you press the switch. That means in here, you are always getting a high going in. When you have a high going in, out here, you're going to be having 0, 0, 0, 0, or in other words, 1, 1, 1, 1. That is the case for A0, which is unconnected. Now let us look at another example. What if you pressed one of these switches? If you, for example, press that switch, SW1, we know that there is a 5 here, 5 volts. But because you have pressed, these 5 volts will come and go through that into the ground. When you push that into the ground, it means that now A1 is connected to the ground. And now we should have, this is a 0. Okay, so that means we have an active value going in here, which should give us out here the code for A1. A1 we know is 0001, which would be here, meaning that here we would have 1, 1, 1, 0, the inverted scenario. What if we pressed S9? If we press S9, that means you have a connection there. Now this gives it a path to the ground down here. And if there is a path to the ground, then it means that the value getting in here into A9 is also 0. And if it is 0, then out here we expect the code for 9, which is 1001. The inverted one would be 0110, right? So this can be used in a calculator. It means that, let's say for instance that you want to press on your calculator 2, 4, 7. This is your most significant bit and your least significant bit. Now, when you are pressing on your calculator, you usually start with the most significant bit. If you are doing 247, you start with a 2, you press a 2. In this case, you would come and press SW2 corresponding to A2. If you press SW2, it will give you, if you press SW2, it will connect a 0 here. All the others will be high, and you'll have a 0 here. A 0 here should now encode 2, which would be 0010. Now you come and press, that means you now release switch 2, and you come and press switch 4, SW4. If you press SW4, now you have a 0 here. Every time you release the switch, that goes back to 1. And now you have a 0 here, all others are high. When all others are high, you encode 4. 4 is 0, 1, 0, 0. This is 2, 4. And now you go and release 4. When you release 4, that goes back to 1. And you come and press SW7 to encode number 7, digit 7. When you press it, a 0 goes in there, and a 0 going in there will give you 0, 1, 1, 1. Okay? This is how your normal calculator works, and systems like this, where you're pressing buttons. I'm sure even your old phone, which was based on buttons, used to work like this. We call this a switch encoder. And so in your calculator, you would now encode this value. How then do you display it? It means that you push this value into like a BCD, because we know this is BCD. We have converted our decimals into BCD, but now if we want to display the BCD value, we can use a BCD to 7 segment decoder. Okay, this is how these things actually work together. That in a system you can have an encoder and a decoder. Just to jog your memory, it is this one. So if I have encoded 2 as 0, 0, 1, 0, I come and put my 0, 0, 1, 0, and then this would display it here in this fashion. All right. Good. Okay. Now let us look at how this actually works, because the display, usually you store this information. You can store this information in registers. If you are not going to display, this is not for displaying. This is for storage now. How do you actually, people are writing in my things again. Let me see. Okay, now you should be unable to write in my. Okay. Now let us look at this thing carefully. We have already seen how this works. So we want to press, let us say that we want to press 2, 4, 7, where this is the most significant bit and that is the least significant bit. Let us look at this. This is a decimal BCD encoder. So that means when I press 2, I will have my input here, and you can, this is inverted at this point, and then we invert again to get our normal BCD. So for instance, let us say 2 is 0, 0, 1, 0. That means I'll have 0, 0, 1, and 0. Now this information is moved. These are my registers. We store information in registers. So if I put 2, which can be encoded into 4 BCD bits, I need 4 flip-flops. I need a 4-bit register, and that 4-bit register is made of 4 flip-flops. So I need to, first of all, delete this so that I have some space. Right. Right, so I have 4-bit registers. So that means I can store 2 in here. In the next one, I can store the other value. In the next one, I can store the other value. These are D flip-flops, meaning that whatever is appearing on its input, if it gets the right clock, that input will just go to the output exactly the way it is. You can see that we have Q11 to Q8, Q7 to Q4, and Q3 to Q0. Each of these, and they are in different colors, is a register. Each register is 4-bit, meaning it has 4 flip-flops. And so this technically is a calculator that stores only 3 bits. As you know, your calculator you might be able to do calculations of up to 12 digits or 10 digits or 8 digits. I don't remember quite where. In that case, it means you would need 8 registers, where each register stores a 4-bit BCD code, and a 4-bit BCD code is enough for all decimal values that you press on your calculator. Let us look at what happens here. Here, this is A0. Now, A0 is connected through an OR gate. An OR gate goes into a flip-flop. This flip-flop OS is to remove a contact bounce. You remember how we use flip-flops to remove the contact bounce of a mechanical switch. This is in first year. I think it is in chapter 3 or chapter 5. It is in chapter 5, flip-flops. Now this is a TP, like a propagation of 20 milliseconds. It means that when you do a conversion, it will maintain that level for 20 milliseconds and then go back down to the other level. We are going to see how all this works out. But you can see here that our outputs, this output, that output, that output, and that output will appear at the D inputs of all the registers. In other words, all of the registers have those inputs available at their inputs. And so the question is, we want to know, where do we store 2, 4, 7? Where do we store 2? Where do we store 4? Where do we store 7? So let us look at the operation of this circuit. The operation of this circuit, first of all, we clear. If you have seen how this is connected, this one is actually a ring counter. It is a ring counter, if you remember. As you can see, the output, so you have, this is an X, Y, Z output. As you can see, this value at the output Z, this value is fed back to the input. This is how a ring counter works, and we know that that is quite different from how a Johnson counter works. The Johnson counter, it would be Z inverse going back, but this is a ring counter, so it's Z itself, the output going back. Right, so if this is a ring counter, first of all, we clear the ring counter. How do we clear the ring counter? By pressing the switch. Let's see what happens when we press this switch. Usually before we press that switch, we have a 1 going into here. You can see the 1 comes from that. And obviously it also goes into there. And on this other side, we preset. So that goes into there. Okay. Let me rub a bit. Let me rub out this one. Yes, you can see that before we press this clear, we have a 1 going in here, a 1 going in there, and a 1 going into the preset. And so preset and clear are both active low, and so if you have a 1 going in, you have done nothing. So if we press this key, the clear switch, we have a 0 going in there, meaning we clear this. we clear that, but Z is preset. That means that if I draw my my truth table, I will have, for example, the clock. Then I will have X, Y, Z, and that is initially I have 0, 0, and Z is preset. What is my inputs? They are my outputs here. Like within these ones, I can say what is Q11 to Q8, Q7 to Q4. These are the registers, the 3 registers, and Q3 to Q0. We want to fill this table. Obviously, they are still 0. We can say that they are initially cleared because the reason why they are initially cleared for, okay, let's just assume that they are initially cleared so that we don't waste time on that. 0, 0, 0, 0, and so everything, all those flip-flops are 0, 0, 0, 0, 0. Now, let us get the first clock or the first switch. Let us call it our first switch. There is actually yeah, there is a clock signal, but as you can see, the clock signal comes from this side, and so the clock signal is the output of this contact bounce. So let us assume that, for instance, we have pressed 2. As I said, we usually press 2. Now, number 2, press the most significant bit, in this case 2. Now, when you press 2, you're going to have, I need to keep, I think, this low so that I can continue to rub. I'm going to rub that. I have 247. When I press 2, what do I have here? This is 2. I press it here. It connects to 0, meaning that that is active low. I'm going to get 0, 0, 1, and 0. And you can see these are going into the OR gate here. Because there is a 1, okay, 0, 0, 1, 0, all of these inputs are going into the OR gate, but one of them is a 1. That means that I'm going to have an output 1. When I have an output 1 going in here, my Q will go to high. It will go high. Q will go high. No, Q will go high, yes. Now, when it goes high, after the 20 seconds, it will go back low. Because we say that this is contact bounce, it will last for 20 minutes, 20 milliseconds, and then after that, it will go back low. When it goes back, it was high, it goes back low. That is the negative going transition. That NGT goes into here, and into that, and also into that. When you get your NGT with a ring counter, we know that the X, what was here will shift there, what was there will shift there, and what was here will go back to X. That means that now this shifts to 1, that to 0, and that to 0. When that happens, it means that X now is a 1, or in other words, X has moved from a 0 to a 1. If you look at the clock signal of these flip-flops, their clock signal is a PGT. So when X moves from 0 to 1, let us look at X is moving from 0 to 1. You see this line here? You have that line, and that line is going to clock that flip-flop, that flip-flop, that flip-flop, and that flip-flop. Now, because these flip-flops have got the right PGT, it means that this 0010, which was at these lines, now will shift into that. That means our Q11 to Q8 will now be 0, 0, 1, 0. But the others have not, because as you can see, for instance, Y has moved from 0 to 0, so that is not a PGT. Z has moved from a 1 to a 0, that is not a PGT, that is an NGT. Obviously, Z, if you notice, it will clock these ones, and Y, which is this one, will clock these ones. And so we still have 0, 0, 0 and 0, 0, 0, 0. Let us look at the next one. When the next thing happens, now obviously pre-sale MSB data shifts, as we have seen, to Q11 to Q8. Now 3, press 4. When you press 4, what happens? Now when I press 4, I am going to have, I think this is at the output 0, 1, 0, and 0. Yes, that is 0, 1, and 0, 0. This 0, 1 appears at the inputs of that, and of that. But because it goes through the OR gate, the OR gate will also once again produce a 1. That one forces this one to move high for 20 milliseconds. After the 20 milliseconds, it moves low, giving another NGT. That NGT will clock this ring counter. When it clocks the ring counter, it will count again, meaning that now that 0 shifts to X, X goes to 1, and this 0 comes to that one. Now, if you look at Y, we can see that Y has made a transition of 0 to 1. 0 to 1 is a PGT, and so if we follow Y, we can see that because Y is clocking these blue, no, these are the green flip-flops, this information will now come and be stored in these flip-flops. Okay, so that means now Q7, no, Q11, Q8 is not affected because it would be affected if X got a PGT, but it is not affected. So that means this one will stay 0, 0, 1, 0. And now Q7 to Q4 will take on the values 0, 1, 0, 0. And that will still be 0, 0, 0 because it still hasn't been affected. If we repeat this operation, once more, we press 7. When we press 7, we know what is going to happen. 7 is a 0, 1, 1, 1. And because you have 1, 1 is coming into the OR gate, you get a 1 here. This thing will give you a PGT after 20 milliseconds. That PGT clocks the ring counter. The ring counter now becomes 0, 0, 1. Now we can see that Z has made a transition from 0 to 1, which is a PGT. A PGT at Z will come and clock these blue ones. All the others will not be clocked because, as you can see, there is no PGT transitions on that side. And so because these ones, this value of 70111 is existing on these lines, this information will be clocked into that. And so data shifts, in this case, 4, you press 7, data shifts to Q3, Q0. Here data shifts to Q7, Q4, right? Now, obviously, if you press again, then we have a problem. But because you are pressing only 247, you don't have to press again. And now we can see that our most significant bit 2 is stored here. Our middle value is stored here, and our least significant bit is stored here. If I needed to store 2475, for instance, I would need another register down here, and in this case 5 would be my least significant bit. So this is a little bit complicated, and I want you to go and try to understand it. But yeah, I want you to, when you look at these large diagrams, not to be scared. I want you to really try to understand what is happening there. I might even bring something like this, maybe draw the diagram for you and ask you to draw the truth table. I'll just give you what I expect you to include in the truth table. And so please don't be afraid to look at some of these large diagrams. Now we are going to have a short break of about 5 minutes. We can regroup here at 8 past the hour. Please don't go off, just you can stay on, and when I return, I'll just go straight. Um, okay, I'm back. Hopefully you've had a rest uh, and you are already back. Now we can move on to multiplexers. Multiplexers are quite easy actually, because for them you have many inputs, but you only want one output. Okay, so out of 10 inputs, you want to select one output to send to the to whatever. So that is also called a data selector. So you have like n inputs, and only one of these n makes its way to the output. As you can see, you can keep shifting this. You shift that, in the next moment you shift it, you shift it, you shift it. And so this is what a multiplexer is. Multiplexers find a lot of functionalities in so many areas. For those of you in telecom, for instance, who know about FDM and TDM, in TDM you share time or time slots. So you can get one channel and divide it into maybe in GSM they divide this into 8 time slots. So it means that within one channel 8 people can use that channel. Each person is given a small time slot in which to transmit their information. And so this is person A, person B, person C, person D, person E. In the case of GSM it would be 8. And so at one moment in time, person A is selected to transmit. In the next moment, person B is selected. In the next moment, person C. Usually these signals are there, but it is the connection that is not there. And that is what the multiplexer is. It does. The multiplexer, if this is my multiplexer, its pointer will point here. Then it will shift that to that point. It will shift that to the next point, meaning that it goes round and round, making sure that everyone gets a chance. That is a multiplexer. It means in one moment in time, only one output goes into, only one input is allowed to go to the output, and in the next moment, another one can be allowed. Now, when we look at multiplexers in this case, we need to find a way of selecting this. How do we do the selection? And so for the selection, we use what we call select inputs. These are also called addresses, the address input of the selected of the input. So you have some value that represents which input you want to allow to go to the output. If we were to look at a scenario like a select input, let's say for instance that we have two inputs. That would be a two input multiplexer. We have our multiplexer here. We have two inputs, which I can call A and B, and my select input is S. Now, usually because we have just two inputs, the select inputs can be like one value or two values. These are just two inputs. So I can say that when S is 1, let B go through, and when S is 0, let A go through. And so I have only one output, which I can call Z. That means that my Z is equal to S. If S is 0, Z is A, and if S is 1, Z is B. So that means that my Z is S, I think it is SB or S inverse A. In other words, yeah. So SB or S inverse A. So that means that when S is 0, Z is equal to, as we can see, this would go out and we remain with A. And if S is B, no, if S is 1, we can see that that part will go out and we have our Z is equal to B. So then you use S to select which of the two inputs actually goes to the output. And so really multiplexers can be easy like this. Let us look at this. This is a two input multiplexer that we have just seen. You can see you have your two inputs, I1 and I0. I1, they are going into AND gates, but your select input goes into gate 2. Gate 2 has I0. It goes into a gate 2 inverted, and in that case it is not inverted. So then you have that SZ is equal to, as you can see, you have your L gate here. And so we are adding, we are ORing, so to speak. We have S I1 plus, in this case, if this is S, then that's S inverse I naught. And this basically is the truth table that we have looked at, where S is 0. If S is 0, you have a 0 going in, meaning you have a 0 here, and that 0 here becomes a 1, and that becomes I1, meaning that that I1 or 0, I1 goes through to the output. This is the case of a 4-input multiplexer. Multiplexer can be denoted as MUX or abbreviated as MUX. If you go through the, and now because we have 4 inputs, we need to select inputs. Because one select input is not going to cut it. We have 4 inputs, so we need to select inputs S1, S0, which can change from 00 to 01 to 1 to 1, 0 to 1, 1. Each of these, so for instance, when S1 and S0 is 00, we should have our output I0, I1, I2, and when they are both 1, it should go to I3. And so your equation can be Z is equal to, if we look here, we can see that it is S1, S0 inverse I0. For this one, it is going to be S1 inverse S0 I1 plus S1 S0 inverse I2 plus S1 S0 I3. You can see that depending on whatever combination of inputs, all 3 of these terms will go to 0 and will remain with the other term giving us the output. Does it? Maybe it's not. It doesn't look like it, although it could be. No, it doesn't look. It almost, I don't know, an XOR gate. So Z is equal to A. That is XOR gate. No, it doesn't look quite like it. This is an 8-input multiplexer. Its equation will be a bit more complicated, but this one actually is the 74 ELE3103. We are going to see some applications of these in a moment. It gives you 2 inputs, it gives you 2 outputs, Z and its inverse. So you can see that you have things coming in here into the NOR gate, and you have your inverted value, and you invert it again to get the normal value. But so to speak, because now you have 8 inputs, we need 3 select inputs. Because we know that 2 to the power 3 is 8. That means that each of those inputs can be selected by a unique code of select inputs. And so we have our select inputs here. This one also has an enable input. It's enable here as a 0 so that it's active low, so that it's inverted to a 1, and that 1 goes into all of these AND gates. If you enable, you make sure that if you want to disable the whole thing, you make E is a 1 so that it can convert to a 0, and the 0 going into AND gates would simply force everything to be 0. So let us look at an example here. Yeah, if E is high, that means it is going to deactivate the whole multiplexer. We don't even care what the select inputs are. We are going to have Z will be stuck low, and obviously its inverse will be stuck, will become high, right? S2, S1, S0, and Z. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. We know that 1, 1, 1 should be selected, should select I7. That will be I6, I5, I4, I3 in that case, I2, I1, and I0. right? So we can see that depending on the combination of your S2, S1, and S0, we will have a certain output that corresponds. Just one output will be left to go out to the output of the multiplexer. Now, if we wanted to do the thing I just spoke out about earlier, where we want to put I0, then I1, then I2, all the way to I7, obviously then we go back to I0, I1. If we want to do like that in a round robin way, in a sort of periodical way, then we can connect, instead in this case, we can connect a counter. We can connect a 3-bit counter, because we know that a 3-bit counter will count from 000 to 111. And then we give it a clock signal, and a clock signal is obviously periodical. It's a periodic signal. And so it will be the one generating these values S2, S1, and S0. And so you will keep changing in this. When you reach here, you'll go back to that and go back to that. And so you can continue seeing your I0, I1, I2, appearing at the output in sequence. Okay. Let us look at this example. How does this work? Here we have, these are the 8 input multiplexers, the 151. This is your 151, as you can see. You have your 8 inputs. You have your enable input, and you have your 3 select inputs, and you have an output that is low, inverted, and your normal output. So now they have been connected in this way. You still have your select inputs and your select inputs. As you can see here, they all come from the same place. Now this enable is connected to S3. Before we had S2, S1, and S0, but now we have added S3 to enable or disable. Now if you notice here, our S3 goes into here, and in this case, it is inverted. Okay, so that means that whatever value of S3 it is, it will enable one of these multiplexers and disable the other IC. So for instance, if S3, and I'm going to call this M1 and M2, if S3 is 0, a 0 going into this bubble will enable M1, but now it is inverted, meaning it disables M2. Enable M1. If S3 is 1, enable M2. Now we have our inputs I7 to I0 and I7 to I0. I could perhaps say that I can rename this one to I8 and I16, I15, sorry, into I15. So you can see that when M1 is enabled, M2 is disabled. That means that these inputs can go through to X. And when M2 is enabled, then these inputs cannot go to X, but these ones of the second of M2, these ones can go to X. Let's try to do a truth table and see. So I have S4, S3, S2, S1, and S0. And then I'll have and I can have my X. I'll say enable. So we know that we can start from S4 as 0, 0, everything. Why did I have S4 here? It is 0, 0, 0, 0, all the way to 0, 1, 1, 1. In this case, M1 is enabled. And so my X, in the case of S3 as 0, and I know 0, 0, 0, for example, I am going to have I0, then I will have I1 all the way to I7. Okay, that is one part of the truth table. And now the next value here is actually 1, 0, 0, 0. When I have 1 here, this is disabled and that is enabled. That means M2 here enabled. And this will continue to 1, 1, 1, 1. And my output here should be I8 all the way to I15. 15. So what I've created here is you have combined two 151 maxes to create a create a 16 input multiplexer. Each of these are 8 input multiplexers, but when you combine them in this fashion, you can create a 16 input multiplexer. Okay, good stuff. Today, I feel tired already. Let us look at this one. This is the quad 2-input multiplexer. It's a 2-input multiplexer, but each of those 2 inputs is a quad. It's 4 bits, so to speak. And so let us start here by understanding it from this IC. So this is the 7FLS157. You have 2 inputs, but these inputs are not 1 bit, but they are words, okay? Word and word. They are 2 words, and so we are looking at them as each word as an input. And this is why the multiplexers have these big arrows. This big arrow shows that it's not, may not always a bit. That input could be a word, as we can see in the quad 2-input multiplexer. So even the output is a word, as you can see. So you have enable, and if enable needs to be 0, because if it is not 0, then you are in problems because you cannot multiplex. Now, if S is 0, then this input will go to the output. This case, S is 0. And if S is 1, then that output is going to go to the output. You can see that when this is high, S doesn't matter because our output will always be low. However, if S is, and so we need to enable by putting is as 0. That means when S is 0, we get our first word going through to the output. And when S is 1, we get our second word going through to the output. Let's see how this might work. Let's say in this case that S is 0. If S is 0, here it becomes 1. And if that becomes 1, this becomes 0. If it is 0, you can cancel that. That one goes there. You can cancel that. You can cancel that. You can cancel that. And so you can see that I1 is going in here. Now these are the correct ones. And so I0, because this is a 1, that's a 1. And we expect this to be 0, meaning that's also a 1. Then I0 A will go through here and go there. And so here we would have I0 A, I0 B, and so on and so forth. If S were 1, that would have a 0 here, and a 0 here. Now we would be killing this one, no? The yellow ones, and so on and so forth. Okay, so let us look at, if you have no questions, we can look at some applications of multiplexers, which are really interesting. I do like asking questions in my exams about them. The first one is a parallel serial converter. Sometimes when we transmit signals within the system, we want to use parallel conversion. But when we are now transmitting that information across long distances, we want to do it in serial, so that we can use one line rather than, say, 8 lines. Because we can lay fewer lines, that's good. Now you have a 151 multiplexer. You have a register that is an 8-bit register. It has X0 to X7. These inputs, these values from the register are shifted and are connected to the inputs of the multiplexer. So now we want each of these values within the register to have an opportunity to go through the multiplexer. And because the multiplexer only outputs one value at a time, the first time it outputs, it might output X7 or X0. Usually it will output the least significant bit, because you know when you are transmitting information, you start with the least significant bit so that it arrives first. X1, X2, each one will have a chance all the way to x7. Now you can see we have a mod 8 counter, and this mod 8 up counter is a 3-bit counter, because 2 to power 3 is 8. So it would have 3 flip-flops, and it is clocked. So the outputs of that clock, which are 0, 0, 0 all the way to 1, 1, 1, become the select inputs. They become the select inputs. Our enable is connected to 0 so that it's active, so that it is always enabled. And every time we clock, the clock signal is is a PGT. Okay. Every time we clock, we change, so that 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. The clock here, that means my S3, S2, S1, S0 clock. 0, 1, 2. Let's look at an example of this. Before we clock, before we clock, this is our X value. So X0 and X7 is there. Before we clock, these inputs are there. So you can assume that our output, let me say Z, our output is 1, which is, or X0 is equal to 1. The first time we clock, the select, because you see when the select inputs are 0, 0, 0, this X0 is the one that will go through to the output. When we clock, our select inputs change to 0, 0, 1. And when we change to 0, 0, 1, we take the next value, which is X1 is equal to 0. And then 2, the next value is 1, which is X2 is equal to 1, and so on and so forth. So because X0, X1, X2, these are coming out one at a time, that becomes a serial value. So you can see that our input now, our output Z is that, which is 1, 0, 1, and this is in serial. Right? So this is how you can connect this to convert your parallel signal into a serial signal. As you can see, this is a register, and so this information is stored here in parallel. Okay, it is available there at the same time, but we are using using a counter to generate our select inputs, and this multiplexer, we are able to extract 1 bit at a time, and so because of that, we can convert that into serial. This is the other interesting one. This is the other interesting one, which we can use to convert logic functions. So when you have like your output Z is equal to ABC plus ABC. Yeah, we can do that. We can use that to you can use a multiplexer, because usually we use gates. So you have inverters and whatnot, and AND gates and OR gates. But in this case, we can use a multiplexer to actually implement that logic function. Let us look at an example like this one. We have a truth table, and we can see that Z is 1 when we have CB as 001 and 010, and the case of 111. This case, that case, that case. This is actually the logic function, and you cannot simplify this logic function further. So how can we implement it using a multiplexer? First of all, the inputs of the logic function become select inputs. So our CBA comes here, S2, S1, S0 become CBA. Now, after doing that, we know which combinations of S2, S1, and S0 give us a high. Find combinations of S2, S1, S0 that return a high output. Because if we know which combinations return a high output, then we can ensure that at the output of the multiplexer we have a high. 2, 3. Do the same for a low output. So now let us see. In this case, we can see that when Z is 0, 0, 0, we need to ensure that I naught at the output, this is I naught, I1, I2, all the way to I7. So in other words, when we have our select inputs as 0, 0, 0, our output I naught is a 0. So when I naught goes to the output of a multiplexer, it should be a 0. So you can see, first of all, that E is enabled, meaning it's connected to ground because it is active row. Now, I naught, we have connected it to ground. Why? So that it is a 0. So that if our S0, S1, and S2 are both 0, 0, 0, meaning they are selecting this value, when this value crosses to the output, it is a 0. So that it can give us that. The case for I1, when CBA is equal to S2, S1, S0 is equal to 0, 0, 1. 0, 0, 1 selects input I0, which is a high. This is a high, the output Z. For this case, Z is 1. And so we connect Z, I1 needs to be connected to a high, so that when we select I1, what passes through to the output is actually high. And so you can see that for the cases of the next one is also high, and the last one, I7, is high. All of the others are 0. The reason is, why are they 0? So that when their select inputs select them, it is a 0 that crosses to the output, because that is the output anyway. It crosses to the output, but for I7, because the output is high, it is connected high, so that when it is selected, you push a 1 out there. Let's see. What if I had Z is equal to, okay, I'll have S2, S1, S0, which is like CBA, really. I know it's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And this is my Z. And I can say that I have a 1, I have a 0, I have a 0, a 1, a 1, a 0, a 0, a 0. Okay? I don't know what this gives me. Maybe it gives me Z is equal to A inverse. Let me say C inverse, B inverse, A inverse, plus C inverse BA, plus C B inverse A inverse. Yeah, that's it. I don't know if you can simplify this, but I think you can if you look at that case and that case. I think you can simplify that. But we want to look at this. You see, the multiplexer will implement this thing, even though it is not simplified. And so you would have your 151 multiplexer, which gives you output Z. And here you have 1, 2, 3, 4, 5, 6, 7, 8, which is I0, I1, I2, I3, I4, I5, I6, I7. Then you have your enable input. This is E connected to ground, E bar. And then you have your select inputs, which are S3, S2, S1, S0. Now, this one needs to be connected high. The reason is that when we select, when our S input, select inputs are 0, 0, 0, we should push a 1 to the output here. And so we should connect this high. Maybe you can put a resistor plus 5 volts. When it is 1, we should connect it to 0. So that when we select, when we have our select inputs as 0, 0, 1, the output is 0, meaning that that 0I1 will be selected and it will go to Z. The same thing with that one, but I3 is high, and so is I4, but I5, I6, and I7 are both 0. Okay, so this is how I would implement my output, my logic circuit that is described by that truth table using a 151 multiplexer. Okay, I have, before we complete, I have this last one. This is called data routing. Maybe I'm going to leave this one to you, but I'll just give a small description of of how this works. You can see that we have two counters. These two counters are made of different counters. So counter one is a combination of two counters, which is 4-bit here and 4-bit there. In other words, the whole counter is 8-bit. This counts units, that counts tens. So units is like 0 to 9 and tens are 0 to 9. So it means you could count from 99 all the way to 0, 0. Okay, this is what that counter does. And now if you want to display this, you have to find a display for that value, the tens, and also for that one, the ones. All right. Now you can see that what he does, what they do here is that the values from this first part of the counter go into this. Now we are using a two input, the quad 2 input multiplexer. And so this word goes into there, and that word, now we have another counter 2. That word goes into here. Whereas the second value of this word goes into the other multiplexer, and that one comes into that multiplexer. You have a BCD 7-segment decoder so that you are able to display your 9 here and your 9 there. So how do we manage to display? Let's, for instance, say that select, counter select. Let's say that select is 1. If select is 1, we are going to select this value and not that value. You remember how we were doing the quad 2 input multiplexer. We select this one, and in the other counter, once again, we will select this one and not that one. That means that this part of that counter will go through and get displayed here, and the other part of the same counter will go through and get displayed here. If our S was 0 instead, we do not select that, we select this, and on that side we select that one. Yes, but as you can see, this is the tens, so the tens will go through and get displayed here, and the ones of the same counter will go through and get displayed there. Please do some bit more reading about this, and next time we will look at how to demultiplex and go to something new in our progression on the course. Have you finished doing groups? Can you submit them? Hello? Let's see if it is okay. The chat is showing. Yeah, we finished. Okay, so if you finished, one of the class representatives can send them to my email. Maureen, I know some of you, I would prefer that the whole thing is compiled for all the classes, and please do give them to, I think Maureen knows my email probably, or Ouma, is it Ouma? One of those guys. Just send them to me, and then we can move on. Yeah, Sylvia, last week we looked at the application of decoders in memory registers. During reading, I feel it's not in chapter 8. It should be in chapter 9. You'll find it somewhere there. I've not, or maybe, I don't know, maybe chapter 7. I don't know, but I've not considered chapter 8 yet. We'll probably come back to it before the course ends. I usually teach it last after I've taught all the important things. Okay. Okay. See you soon.